Hello friends, I am Dr. Sudhan Sharma from School of Computer Information Sciences, Indira Gandhi National Open University. In our last session, we had explored the concept of the scalar product, that is dot product, and we also learned about various properties of the dot product. Apart from this, we understood about the projection of one vector on another vector, and we solved ample number of numericals. Now, in this session, we are going to extend our discussion towards the cross product, and we are also going to discuss about the scalar triple product and the vector triple product. The objectives of today's session are to define the cross product or the vector product of the vectors. Apart from this, in this session, you are going to learn the usage of cross product to find the area of parallelogram and define the scalar product and the vector triple product. Now, to begin with, vector product or cross product of the two vectors A and B is represented by the expression A cross B. Now, A cross B is nothing but magnitude of A, magnitude of vector A into magnitude of vector B into sine theta into unit vector n. The dot product was a scalar component. That's why it was called scalar product, and the outcome of the cross product, that is a vector product, is a vector component. That's why along with AB sine theta, we are having a unit vector n. But in the case of the dot product A dot B, we were simply having the expression magnitude of A into magnitude of B into cos of theta. The expression was not including the unit vector, and that's why the A dot B component was scalar and A cross B is vector. Now, in order to have the better understanding, let's understand what cross product means. We already know by the expressions of the trigonometry that sine theta is nothing but perpendicular upon hypotenuse. Say, referring to this figure, say B is a vector which is subtending an angle theta on vector A, then the horizontal component of vector B will be given by B cos theta, and using B cos theta, that is the horizontal component, we can determine the dot product. But so far as the vertical component is concerned, the vertical component will be given by B sin theta, because the perpendicular represents the vertical component. In this triangle, the hypotenuse is represented by B, and this is equivalent to sin theta. So, that means the perpendicular component will be equal to B sin theta. So, B sin theta is actually the component which is perpendicular to vector A. So, B sin theta, if B is this vector subtending angle theta, then the component B sin theta, which will be this vector, this part will be perpendicular to vector A. So, that means the product of the vertical component of vector B with the vector A is actually representing the cross product, and the cross product is perpendicular to both vectors, vector A and vector B. Referring to this figure, say we stretch our finger and thumbs such that, let me show you, if I stretch my fingers in such a manner, then this thumb expression, say this expression, this finger is representing say vector B, the index finger is say representing vector A, then the cross product of the two vectors is given by A cross B. Now, we already learned that if B is pointing towards me, then the negative of B will point away from me. As a result of which, what will happen? This is the situation. Now, the thumb is pointing down. So, that means A cross B is not equal to B cross A. So, the direction is totally reversed, and this is nothing but, you can say that this is a right-handed system. In the right-handed system, say we assume that the middle finger represents vector B and the index finger represents A, then the thumb stretching all together in the manner shown and in this session, you can find that A cross B is the direction of the vector A cross B. And if I reverse the direction of vector B from this side to this side, then the direction of A cross B turns downward. So, A cross B is the mathematical expression is magnitude of A into magnitude of B into sine theta, where A and B are two non-zero and non-parallel vectors. They are not collinear. Okay. So, you can say that, and n is the unit vector. So, if somebody wants to check that whether vector A and B are parallel to each other, then if they are parallel to each other, then theta will be equal to 0. If theta is equal to 0, then obviously sin theta, that will be equal to sin 0, and it is equal to 0. So, if we are supposed to check whether the vectors are perpendicular to each other, then in that case we are supposed to determine the dot product. If dot product turns out to be 0, then the vectors are perpendicular, because cos 90 degree is 0. But if we want to check whether the vectors are parallel or they are collinear, then we need to check for the cross product, because if the vectors are parallel or collinear, then theta is equal to 0 and sin 0 is equal to 0. That means this is the proper test to check whether the vectors are parallel or perpendicular. So, so that means if we are having a vector A and we are going to take the cross product with the same vector A, then this means that the theta is equal to 0, and since sin theta is equal to sin 0, in this case will be equal to 0, that means A cross A will turn out to be 0. This is one of the important properties of the vector product. Second important property is A cross B is equal to minus of B cross A, and you can say that A cross B is not equal to B cross A. As it is already discussed in this figure also, it is shown that if A is representing the index finger and B vector is representing the middle finger, then A cross B is represented by the thumb, which is pointing upwards, and this is the situation. And if I reverse the direction of B to minus B, then the direction of A cross B turns down. That means direction of A cross B turns to minus of A cross B. That means A cross B is equal to minus of B cross A, and we are having A cross B is not equal to B cross A. Apart from this, as we had already learned in the case of the dot product, that we had I dot I is equal to J dot J is equal to K dot K is equal to 1, but other identities I dot J or J dot K turns out to be 0. We learned all these things when we were discussing the dot product. Same type of relations exist for the cross product, and it says that I cross I is equal to J cross J is equal to K cross K is equal to 0, because the subtended angle is 0, and we are just referring to this expression A dot A. So, that means if we are taking the dot product of the unit vector with the same unit vector, then the angle between the two is 0, as a result of which sin 0 is 0. Hence, I dot I, J dot J, or I cross I, J cross J, K cross K all will turn out to be 0. So, this is the first important property, but I cross J, J cross K, K cross I will be the remaining. I cross J will turn out to be K, J cross K will turn out to be I, and K cross I will turn out to be J. Let me explain you how. So, if we are moving in this direction, that is anti-clockwise direction, you can say we are moving from I to J. So, what will be the outcome? The outcome, if we are say moving from I to J, so the pen will be pointing towards, if I say refer to say the pen, and if I move the rotate the cap of the pen in a anti-clockwise direction, then the cap will move towards me, So, that means if I move anti-clockwise direction, the cap will move away from me. So, if I take I cross J, that means I am moving in the anti-clockwise direction, as a result of which the cap will move towards me. So, it is moving towards the vector unit vector K. So, I cross j will move towards unit vector k. But if I rotate it in the other direction, if I rotate it in the other direction, in this direction opposite, that is the clockwise direction, j cross I, then automatically the cap will move away from me. So, that means j cross I will be equal to minus of k. So, that is why just hold your pen and move the cap in the anti-clockwise direction, and you will get all the identities that I cross j is equal to k, j cross k is equal to I, k cross I is equal to j. Let me show you again. So, this is I, this is j, this is k. If I move from I to j, the movement will be towards k. That is why I cross j is equal to k. If I move from j to k anti-clockwise, the movement of the pen will be towards I. So, j cross k will be equal to I. Similarly, if I move from k to I in anti-clockwise direction, then k cross I will be equal to j. And if the direction is j cross I, then it is towards negative of k, away from me. K cross j, that means negative I axis, and I cross k, that is negative j axis. So, you can always refer to this diagram, and you can always determine that what is I cross I. It will be I cross I, j cross j, k cross k will be 0, whereas I cross j is equal to k, j cross k is equal to I, and k cross I is equal to j. So, the fourth property is that if there are two non-zero vectors A and B, then they are parallel. When they are parallel, if their cross product is 0. If the cross product of the two vectors turns out to be 0, that means the two vectors are parallel to one another. This is the vector A and this is vector B. The angle between the two will be 0, as a result of which sine of 0 will be equal to 0. This shows that the two vectors are parallel to one another. So, the next property is that the vector product is distributive over the addition of the three vectors. Likewise, A cross B plus C can always be expressed as A cross B plus A cross C. We had just opened the braces. Similarly, we can write that A plus B cross C is equal to A cross C plus B cross C. Apart from this, one more property is there. If lambda is a scalar and A and B are the vectors, then lambda times of A cross B is equal to A cross lambda times of B, and is this same as lambda times of A cross B. And you remember that A is a vector say along x axis, B is a vector say along z axis, then A cross B will be the vector along y axis, and A cross B is represented into the plane bounded by A and B. Now, we discussed the component form of the dot product, that is the scalar product. Now, it is the time to discuss the component form of the vector product. Say we are given two vectors, vector A and vector B, wherein the vector A is say A1i plus A2j plus A3k, and B vector is given B1i plus B2j plus B3k. Now, over here we are going to explore these identities which we had already discussed as the properties in our past slides, wherein we learned that I cross I is equal to j cross j is equal to k cross k, all are 0, but I cross j, j cross k cross I, all are say I cross j is k, j cross k is I, k cross I is j. So, opening the braces, though I will be we are supposed to multiply it point wise, that is I will be multiplied by I, then I will be multiplied by j component, I will be multiplied by k component. So, that is why we are going to get the cross product of I cross j, I cross k. Similarly, we are going to multiply the j component with the other components of the vector. That means j component will be multiplied by I, cross product with I, j cross product with j, k cross product with k. So, j with cross product I, j cross product j, j cross product k. Similarly, k cross product I, k cross product j, k cross product k. And we know that k k cross k, I cross I, and you are having j cross j. These all are 0. These all are 0. And we know that I cross j is equal to k, I cross j is equal to k, similarly j cross I, and all those things we are using these identities. So, the expression will resolve to this one. So, that means if we see the expression closely, we find that this expression is nothing but turning out to be the determinant representation of the components of vector A and B. Because if substituting these values, that I cross j is equal to k. So, the I cross j is equal to k. So, you are finding A1 B2 into k. So, A1 B2 into k. Similarly, I cross k is minus j. So, I cross k is minus j. So, the A1 B3 minus j. So, following the same pattern and then rearranging the equation, that is collecting the I the values for the I unit vector, j unit vector and k unit vector, this turns out to be this expression, and which is nothing but the determinant representation of the components of the two vectors A1, A2, A3, B1, B2, B3. So, that means if we are aware of the component form of the vectors, that is A is equal to A1 I plus A2 j plus A3 k, and B vector is equal to B1 I plus B2 j plus B3 k, then the component form of the A vector cross B vector will be given by I j k, and this A1 B1 are the component for the I unit vector, A2 B2 are the component for the j unit vector, A3 B3 are the components for the k unit vector in the respective vectors A and B. Computing the value of this determinant, you are going to get the value for A cross B. So, let us apply this understanding. Find A cross B if A is equal to I plus j plus k and B is equal to I plus 2j plus 3k. So, simply we need to determine the value of the determinant. So, we just simply write the determinant I j k and put the components 1 1 1 for vector A and 1 2 and 3 for vector B. So, I hope you remember that how to solve the determinant, and we learned that this determinant will turn out to be I into 3 minus 2 I, this is the intersection point is I, and this into this minus this into this. So, 3 minus 2. Subsequently, we are going to concentrate now on j, that means the second component, and we are going to get 3 into 1 minus 1 into 1. So, minus j 3 into 1 minus 1 into 1 is this, plus k 2 minus 1. So, this turns out to be I minus, because 3 minus 2 is 1, 3 minus 1 is 2 and 2 minus 1 is 1. So, this turns out to be I minus 2j plus k, I minus 2j plus k. So, this is the vector A cross B, A cross B. Now, let us solve one more numerical. Find the unit vector perpendicular to both vectors A and B. So, unit vector perpendicular to both vectors. So, that means again we are supposed to find A cross B, because A cross B is the vector which is perpendicular to both vectors A and B. So, magnitude of A cross B on the same lines you can determine by substituting the value of A1, A2, A3. A1, A2, A3 are 4, minus 1 and 3, B1, B2, B3 are minus 2, 1 and minus 2. Substituting the values and solving, you get the value of A cross B as minus I plus 2j plus 2k. Now, the question is about to find the unit vector, and we know that A magnitude of A into A unit vector is equal to vector A. So, that means A unit vector is equal to A vector divided by magnitude of A. So, because we are over here to find the magnitude of A cross B. So, that means magnitude of A or unit vector for A cross B say we are writing this as unit vector, say this, then this will be A cross B upon magnitude of A cross B. So, what will be the magnitude of A cross B? Since the vector A cross B turns out to be minus I plus 2j plus 2k, therefore, magnitude of A cross B is equal to square root of minus 1 square plus 2 square plus 2 square, which is this value, and this turns out to be square root of 9, that is equal to 3. Therefore, the unit vector, say A cross B unit vector, will be equal to A cross B upon magnitude of A cross B, and magnitude of A cross B is 1 by 3 is 3. So, 1 upon A cross magnitude of A cross B is 1 by 3, and A cross B is nothing but this. So, this is the unit vector A cross B. Now, let us discuss one important question, wherein we are going to apply the properties of the determinants. So, again I am emphasizing that the material, the content given in self-learning material, the units are interconnected. The understanding of one unit is to be applied into the other unit. Likewise, over here we are solving the problem of vectors, but we are using the properties of determinants. We are into the fourth block, but we are applying the understanding of our first block and the first unit of the first block, that is the determinants. So, the question is, prove the distributive law A cross B plus C is equal to A cross B plus A cross C. Now, the given vector A, B, C are A1i plus A2j plus A3k, B1i plus B2j plus B3k, C1i plus C2j plus C3k. So, B plus C, by adding these two vectors, you can always get that B plus C is B1 plus C1i, B2 plus C2j, B3 plus C3k. Therefore, A cross B plus C will be given by the determinant I, j, k, components of A, that is A1, A2, A3, and components of B plus C, which are B1 plus C1, B2 plus C2, B3 plus C3. And we learned that in this case we applied the properties of a determinant, and this determinant can always be written in this format, wherein the component B1 and C1 are segregated, and we got the expression Ijk A1 A2 A3 B1 B2 B3 plus Ijk A1 A2 A3 C1 C2 C3. So, this represents A cross C and this represents A cross B, and we had proved that A cross B plus C can always be expressed as A cross B plus A cross C. So, again one more numerical for your better understanding to connect the understanding of cross product and dot product. Over here we are applying the understanding of dot product and cross product, and we are here to find the magnitude of A cross B, vector A cross B, wherein vector A is given, the magnitude of vector A is given 10, magnitude of vector B is given to us as 2, and we are given A dot B is equal to 12, and we are supposed to find A cross B. So, we are given A dot B, but we are supposed to find A cross B magnitude. So, we know the expression that cos theta is equal to A dot B by magnitude of A into magnitude of B vector. So, A dot B is given to us, A dot B is given to us as 12, magnitude of A is given to us 10, and magnitude of B is given to us 2. So, this will turn out to be 12 upon 20, and this is nothing but 3 by 5. So, this is the part. Now, we know that sin square theta plus cos square theta is equal to 1, and rearranging this identity you can say that sin theta is equal to square root of 1 minus cos square theta. We determined already cos theta. So, using this into this expression, that is sin theta is equal to square root of 1 minus cos square theta, substituting the value you can get the answer square root of 1 minus 3 by 5 whole square, and this solves to 4 by 5. So, that means the magnitude of A cross B, the magnitude of A cross B, because the expression for vector A cross vector B is nothing but magnitude of A into magnitude of B into sin theta into n unit vector. So, this part represents the magnitude of A cross B, this part represents the magnitude of A cross B. So, the magnitude of A cross B will be given by A into B sin theta. So, we know magnitude of A is 10 units, magnitude of B is 2 units, and sin theta is 4 by 5. So, that means this is equal to the magnitude of A cross B. I hope you understand what is the relevance of understanding each and every concept in detail, because you do not know which concept is going to be applied in which situation. So, in examination also you can have some type such type of numericals wherein you need to apply the understanding of determinants and trigonometry into your vectors calculation. Now, over here we are with another example, and we are supposed to show that A vector minus B vector cross product A vector plus B vector is equal to 2 times of A vector cross B vector. So, just by opening the braces in a normal manner, you can always write that A vector minus B vector into A vector cross product of A vector plus B vector can always be written as A vector A minus B vector cross A vector cross A vector plus A minus B vector cross B vector. Again opening the braces, A vector cross A vector minus B vector cross A vector plus A vector cross B vector minus B vector cross B vector. Now, we know that A cross A is 0 and B cross B is also 0, and we also know that A cross B is equal to minus of B cross A. So, using this property into this expression, you can always write that A cross B is equal to minus of B cross A. So, that means this is equal to A cross B. So, that means this solves to twice of A cross B. So, I hope you understand how we solve this numerical. Now, we are going to understand how to apply the understanding of vectors to calculate, say, area of the triangle or parallelogram, because parallelogram is nothing but the extended form of a triangle. Over here in figure 5, it is shown that, say, there is a vector A which is represented by vector OA, that is OA represents vector A and vector OB represents vector B. So, this is vector B and this is vector A. We learned about the projection part also, that B sin theta will be the perpendicular projection of B, that means this part, this is the projection of B onto the y axis. So, and that means BC, this is the perpendicular projection, this is the projection. So, what should be this projection? This projection should be B sin theta. That means BC should be equal to OB sin theta, which is nothing but magnitude of B sin theta. And we know that the area of the triangle OAB is equal to half of base into height. What is base? Base is OA and height is BC. So, OA is nothing but vector A. So, that means half of magnitude of A vector, and what is height, that is BC, this is nothing but B vector into sin theta, and this is nothing but magnitude of A cross B. So, half of magnitude of A cross B will be representing the area of the triangle AB, and we know that area of the parallelogram with A and B is given by this dotted expression included, that means this and this. So, that means this is twice of the area of the triangle, twice of the area of the triangle. So, that means area of the parallelogram will be twice of the area of the triangle. So, half of this. So, that means this is equal to magnitude of A cross B as a whole will represent the area of the parallelogram, whereas half of the magnitude of A cross B represent the area of the triangle. So, I hope you understood that how to determine what is the relevance of cross product when we are determining the area of the triangle and the area of the parallelogram. Now, one more thing I would like to emphasize, that say if this is our parallelogram and if we sweep this parallelogram say along in this direction, then it will sweep a geometry, which is nothing but parallelepiped. Now, how to find the volume of a parallelepiped? We are having the parallelogram whose area is given by magnitude of A cross B, we recently learned, and A cross B is nothing but vector A to vector B into sine theta. Now, that means sweeping it into a perpendicular direction, that means we are going to compute the triple product, and triple products are of two types. We are having a scalar triple product and we are having a vector triple product. So, to begin with, let us understand what is the scalar triple product. The scalar triple product is actually we are combining the dot product and the cross product. B cross C is a vector, and if we take the dot product of this vector with vector A, then it is represented as A, B, C, and this is nothing but the vector triple product of the three vectors, and this is represented by A dot B cross C. So, the definition says that if A, B, C are any three vectors, then the scalar product A dot B cross C is the scalar triple product of vector A, B and C, and it is denoted by square brackets A, B, C. Thus, square brackets A, B, C into the square brackets is equal to A dot B cross C, and that means this is a scalar quantity because the final outcome is given by the dot product, This is a vector, and this is also a vector. So, dot product of the two vectors, wherein one vector is the cross product of the two vectors, such a representation is known as triple product, and because the dot product is giving us the output which is scalar in nature, that is why it is a scalar triple product. Geometrically, the scalar triple product is used to determine the volume of the parallelepiped formed by the vectors A, B, C. That means we know that A cross B in the terms of the, if we are knowing the component form, say vector A is equal to A1i plus A2j plus A3k and vector B is equal to B1i plus B2j plus B3k, then we can determine the cross product of A and B by this expression. We had already deduced this expression in our earlier discussions, but the understanding is that the volume of the parallelepiped geometry which is shown over here will be represented by the magnitude of the triple product A dot B cross C. So, that means volume will be given by A, B, C, which is the scalar triple product A dot B cross C. The magnitude of this represents the volume of the parallelepiped geometry. Now, as we had already learned that if we are given a vector A as A1i plus A2j plus A3k and B as B1i plus B2j plus B3k, then A cross B is given by I, J, K, A1, A2, A3 B1, B2. So, on the same lines you can say that A dot B cross C, because we are here to understand about the triple product now. So, A dot B cross C will always be given by the expression A dot the determinant representation of vector B cross C. The determinant representation of vector B cross C will be I j k B1 B2 B3 C and C1 C2 C3, and the triple product part, that is A dot B cross C, will be given by vector A dot this geometry, this which is this part, and this turns out to be this is simplified only to A1 A2 A3 B1 B2 B3 and C1 C2 C3. So, this is the final formula. So, this is the formula, and let us learn that how we achieved this formula. So, that means A dot B cross C, simply you need to put the components of I, j, k unit vectors into their respective column. This column is for vector I, this for vector j, and this is for unit vector k, and solve the determinant. So, let us understand how we got this answer, this formula. So, vector A, so we represent the component form of vector A as this, and this is the determinant, we expanded the determinant as we had discussed and we learned so many times in our earlier sessions also. So, expanding the determinant and then multiplying it component wise, that is I with I, j with j, k with k. So, because the dot product, we know the property I dot I is equal to j dot j is equal to k dot k is equal to 1, because theta is equal to 0 and cos 0 is equal to 1, because A vector dot B vector is equal to magnitude of A magnitude of B cos theta. We learned about this much. So, when I component multiplied with the I component of B cross C, which is this B cross C, the I component is this, the j component is this, the k component is this. Multiplying the I component of A j, multiplying the I component of A vector, that is A1, A2 and A3 with the I j k component of the vector A B cross C, you will get this expression, and this expression is nothing but your determinant A1 A2 A3 B1 B2 B3 and C1 C2 C3. So, that means A dot B cross C is nothing but this determinant. I hope you understood how to determine the scalar triple product of a vector, and there are some of the properties of the scalar triple product, and the first and the foremost property is that ABC is equal to ABC is equal to BCA is equal to CAB. That means A dot B cross C is equal to B dot C cross A is equal to C dot A cross B. And because we learned that A cross B is equal to minus of B cross A, so we can say that B dot A cross C will be negative of B dot C cross A. So, BCA is equal to minus of BAC, because C cross A, this is B dot C cross A, and this is equal to minus of B dot A cross C. Why? Because C cross A is equal to minus of A cross C. So, that means A dot B cross C is equal to B dot C cross A is equal to C dot A cross B, but this is negative of minus of B dot A cross C, negative of C dot B cross A, negative of A dot C cross B. Next important property of the scalar triple product A dot B cross C is that you can say that A dot B cross C can always be represented into the square forms, that is A comma B comma C, B comma C comma A and C comma A comma B, and this is just the repetition of the first part, but the observation is if we are having the dot product in the manner given in property number 3, wherein we are having the scalar triple product of the 3 components, that is PQA, PQA, PA, QB and RC, then the scalar components will automatically comes out. That means PA, because P is a scalar component, dot QB cross RC is nothing but PQR A dot B cross C. So, that is equal to PQR A B C. So, scalar component, the entire scalar triple product is to be multiplied by the product of the scalar components of the independent associated with the independent vectors. So, PQ are the scalars, and again we are having one more important property, that if two of the vectors A, B or C are same, then the entire scalar product turns out to be 0. This is from the properties of the determinants, that if any 2 rows or 2 columns are same, then the entire determinant turns out to be 0. So, if any 2 of A, B, C are same, then A dot B cross C turns out to be 0. If this row is and they are same, then this turns out to be 0. Or this B is same with C, or A is same with B, then any 2 rows are same, any 2 vectors are same, then this turns out to be 0. Now, there is a theorem that if the vectors A, B, C are coplanar, then their scalar triple product, that is A dot B cross C, should be equal to 0. So, if we need to check whether the vectors are coplanar, so we learned if we want to check that whether the vectors are perpendicular, then we need to check the dot product. If we say that the vectors are parallel, we need to check for the cross product. If we want to check that the vectors are coplanar, then we need to check for the scalar triple product. Now, let us solve one numerical. Over here, the vector A is given to us as 7i minus 2j plus 3k, vector B is given to us as 1 minus 2j plus 2k, and C is given to us as 2i plus 8j. That means the kth component is 0. So, we need to calculate A dot B cross C. So, we know that A dot B cross C is represented by the determinants of the independent components of vector A, B and C. Substituting the values of the independent components, that the coefficients of the respective unit vectors, that is A1, A2, A3, B1, B2, B3, C1, C2, C3 into the determinant, you will get this determinant 7 minus 2, 3, 1 minus 2, 2 and 2, 8, 0. Solving the determinant, as we had learned in our earlier session, that how to solve for the determinant, you will get the answer minus of 84. Now, this is somewhat an example of different type, wherein we need to find the value of lambda. Lambda is the coefficient of unit vector I in vector B, and we are given the vectors A, B and C, and it is said that they are coplanar. And we learned that when the vectors are coplanar, then their dot scalar triple product, that is A dot B cross C, should be equal to 0. And that means this A1, A2, A3, B1, B2, B3, C1, C2, C3, this determinant should be equal to 0. So, substituting the values of respective coefficients of I, J, K for vectors A, B and C into this determinant, you will get the and putting it equal to 0, because the scalar triple product should be equal to 0 for the coplanar vectors. Opening the solving the determinant, and you get this expression, and after solving this expression, you will get the value of lambda to be equal to 13 by 15. So, this is the value of lambda, that is 13 by 15, which you simply got by applying the understanding that for coplanar vectors, the scalar triple product should be equal to 0, and we solved simply the determinant. I hope you understood that why we discuss determinants in so much detail, because their application was very much required when we are going to solve for the vectors. Now, there is one more example, say if A, B and C are coplanar, then prove that A plus B, B plus C and C plus A are also coplanar. And we know that if the vectors are coplanar, then their scalar triple product, that is A dot B cross C, should be equal to 0. And we are required that these are also coplanar, so that means A plus B dot B plus C cross C plus A, this scalar triple product should also be 0. So, in order to verify this, we simply open the apply the cross product and the dot product respectively. Likewise, over here, applying the cross product, we firstly take the cross product of vector C with B plus C, then cross product of vector A with vector B plus C. So, taking the cross product of C with vector B plus C, we will get B plus C cross C. Cross product of vector A with vector B plus C, we will get B plus C cross vector A. Then again opening the braces, taking the cross product of C with B, C with C, A with B, A with C, you will get B plus C, B cross C, then you got B cross A, C cross A. Why? Because C cross C is 0. This C cross C, this turns out to be 0, and we are left only with three vectors. Now, we expand the dot product part. So, we take the dot product with vector A. So, with the first vector it will be A dot B cross C, with the second vector it will be A dot B cross A, with the third vector it will be A dot C cross A. Similarly, B will be the dot product with vector B will be taken. So, first it will be B dot B cross C, B dot B cross C, then B dot B cross A and B dot C cross A. We simply just perform normal dot product. Likewise, we perform a normal multiplication in the case of algebra. When we are multiplying, we are opening the braces. This is normal calculation. So, the first expression turns out to be ABC, second turns out to be ABA, ABA, third turns out to be ACA, then BC, BBC, BBA and BCA. Now, we know that ABC is equal to BCA is equal to CAB. Now, we are having BBA, so this will turn out to be 0, BBC, this will turn out to be 0, ACA, this will turn out to be 0, ABA, this will turn out to be 0. So, only two terms will remain, this is the first term and the last term. And by using this identity, this property that ABC is equal to BCA is equal to CAB, this BCA can be written as ABC. So, that means ABC plus ABC, this turns out to be twice of ABC, and it is given that ABC are coplanar. So, that means ABC, the scalar triple product of ABC is nothing but 0. That is why the answer turns out to be 0. This implies that vector A plus B, B plus C and C plus A are also coplanar. I hope you understood that how we solve this numerical. Now, we extend our discussion to one more important concept, that is vector triple product. The scalar triple product was A dot B cross C, and it was scalar because there is a dot product of the two vectors. B cross C is also a vector, but in case if instead of dot product we replace with the cross product, that is A cross B cross C, then this is the vector triple product. And the general expression for vector triple product is given over here, that is A cross B cross C can always be expressed as A dot CB minus A dot BC. We are not going into the derivation of this expression wherein we are deducing the dot product from the cross product, and so this is out of the scope for this session. But A cross B is A cross B cross C is not equal to A cross B cross C. This is the this is self explanatory, as we had discussed n number of properties of the cross product in our earlier session, and this implies that A cross B cross C is a vector which is perpendicular to both, that is vector A and vector B cross C. So, this is an important observation, and B cross C is also a vector which is perpendicular to both vector B and C. So, that means that A cross B cross C is lying into the plane which contains vector B and C, that is A cross B cross C, and vector B and vector C are coplanar vectors. So, A cross B cross C and vector B and C are coplanar vectors. Now, we apply the understanding of this formula, that is A cross B cross C is equal to A dot C B minus A dot B C to solve one numerical. Over here it is given that it is required to show that A cross B cross C plus B cross C cross A plus C cross A cross B is equal to 0. Now, expanding the respective expressions, that is A cross B cross C, B cross C cross A, C cross A cross B, by using this expression 1, we can always write A cross B cross C is A dot C B minus B dot C A, A dot C B minus A dot B C, and B cross C cross A can be expressed on the same lines as B dot A C minus B dot C A. Similarly, A cross B cross C can be expressed as A dot C dot B A minus C dot A B. Now, we know that the dot products are commutative, that is A dot B is equal to B dot A, as a result of which these two expressions, this expression cancels with this expression, A dot C expression cancels with C dot A expression, and B dot C expression cancels with C dot B expression, because the signs are always opposite. The signs are always opposite, because in A dot C this is positive, but C dot A this is negative. So, they cancels out, as a result of which the result turns out to be 0. So, this is verified and it is shown that this is true. And I hope you understood about the concepts of the scalar triple product, vector triple product, and what are the various formulas, how to verify that the vectors are coplanar or not, and this is all about the vectors. And in the subsequent session, we are going to extend the discussion for 3-dimensional geometry. Again, I re-emphasize that understanding of the previous units, previous content delivered in the sessions is very much applicable in the subsequent sessions. You will see that even in 3-dimensional geometry, we are going to explore the concepts of the vectors and determinants also. So, please try more and more problems given into your self-learning material for better understanding. Thank you.